Hi again. I'm going to continue talking about section 4.1. At the end of the last video, I made the point that the end behavior of any polynomial function matches that of the power function f of x a sub n x to the n with the same degree. So what do I mean by that? Well, let's take a look at some graphs. What I mean is to say, notice this graph is f of x equals x to the 6th minus 3x to the 5th, blah, 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 blah. Its end behavior, what's happening, up here and over here on these ends, is going to be the same as f of x equals x to the 6th. Why does that happen? Well, what ends up happening is that this, the leading term, right, which determines the degree of your function, and for this one that would be x to the 6th, it really dominates the value of this whole entire polynomial, right? Because if you're taking a number and multiplying it by itself 6 times, that is a huge number compared to the other terms, like if you only multiply it by itself 5 times or 4 times or 3 times or 2 times. And so that first term really dominates what's happening to the function as x gets really, really big or as x gets really, really small in the negative direction. It's either going to get really, really big itself or really, really small. Okay, so that's why polynomials kind of look the way they do and why the end behavior matches the power function that aligns, with its first term. Yeah. I also want to look at these graphs and think about something else. I want to talk about what we call or what the book, I suppose, calls turning points. So if we look at x to the 6th right here, a turning point is where the function goes from decreasing to increasing or increasing to decreasing. So on this graph we have a turning point here, so that's 1, 2, 3, 4, 5 turning points. Okay, now this function is of degree 6, so let's keep that in mind. Degree 6, 5 turning points. Another function, this is x cubed minus 3x squared minus 6x plus 8. Notice its end behavior. It looks kind of like x cubed, except it's doing some other things in the middle here. It has 1, 2 turning points, right? So you might say, oh, a 6th degree function has 5 turning points. A 3rd degree function has 2 turning points. So maybe it's 1 less than the degree. Well, you might think that until you look at this graph, which is x to the 4th. Notice x to the 4th only changes direction from decreasing to increasing 1 time. So it only has 1 turning point. It turns out that all polynomial functions have at the most n minus 1 turning points. So that's something to keep in mind as you're graphing polynomial functions. As kind of a check, have at most n minus 1 turning points. That is if your function is nth degree, function of the nth degree. Yeah. So it can have all the way up to, but not including, the degree turning points. All right, let's go back to these graphs, and I want to also start talking about zeros. Now, this x to the 6th function has 1, 2, 3, 4 zeros. This x to the 3rd function has 1, 2, 3 zeros. And x to the 4th only has 1 zero. So a polynomial function can have up to n zeros if it's of the nth degree, but not more than that. Yeah? And why would it not have, why would this function, which is a 6th degree function, why would it not have 6 zeros, right? I mean, if we look at the 3rd degree function that I have here, it's 3 degrees and it has 3 zeros, right? Remember zeros kind of align, well, they do align with solutions to that equation set equal to 0. So if you think about, quadratic equations, how many solutions do you get? Well, do you remember learning that quadratic equations have two solutions, but sometimes one of that solution happens twice? Yeah? Well, that's our next kind of idea that we need to think about in studying polynomials, is the idea of multiplicity. Yeah? So, I just want to recall something. Yeah? If I had the equation x squared plus 2x plus 1 equals 0, and I were to solve this by factoring, I know that that factors to the square of the sum x plus 1, right? And we'd say, okay, by the zero product property, then either x plus 1 equals 0 or x plus 1 equals 0. We might not really write it twice, but we could because there are two factors. So we say that x is equal to -1 or -1. We really only get one solution, but it happens twice. That solution happens twice. So what we would say is that -1 is a solution with multiplicity 2, right? That means that it happens twice. All right, so now I want you to also notice something. Notice that if we have a solution to an equation, right, x equals -1, I could always go back and rewrite this by adding the 1 to both sides as x plus 1 equals 0. And if I have two of those, I could also then go backwards and say, okay, well, if I have 2x plus 1 equals 0, I can multiply those x plus 1s together to be 0. And then, of course, if I multiply out that x plus 1 quantity squared, I can get the trinomial x squared plus 2x plus 1, right? So then we can say something like, well, if I have a 0 of a function, if I have a solution of that function with multiplicity 2, then notice right here, x minus that value happens to be a factor of the function twice, right? So let's think about this as a function instead. If I had f of x is x squared plus 2x plus 1, right? I know that that factors to x plus 1 squared, right? And I ask myself, okay, what are the zeros or x-intercepts of that? Well, of course I'm going to get the x equals -1 twice, okay? So what I just said then is I said if r, and the book uses r, is a 0 of the function of a function, and that 0 has multiplicity 2, meaning that it happens to be a 0 twice, right? Then I know that x minus that number is a factor of the function twice. Right? Notice that x minus 1 is the same thing as x minus a negative, x plus 1 is the same thing as x minus -1. So I'm saying that this is my 0, r. It has a multiplicity of 2. And so here's my x minus r as a factor twice. Okay? And it turns out that multiplicity does some really cool things to the graphs of functions. Yeah? Okay, so what we're going to do is we're going to take a look at a new polynomial. Yeah? So this is an example. Yeah, we're going to factor the polynomial f of x equals minus x to the 5th plus 2x to the 4th plus 4x cubed minus 8x squared. And then we're going to find its zeros with multiplicity and find its zeros with multiplicity. And we are going to go ahead and graph this using Google, although this isn't something that you'll have to do in your homework until a little bit later by hand. But we will take a look at it because we want to see something kind of cool. Now the first thing I'm going to notice is that there's a common x squared factor, and since my leading coefficient is negative, I'm going to factor out the negative also. So I'm left with minus x squared times x cubed minus 2x squared minus 4x plus 8. And then I'm going to remember, and hopefully you will too, that this is a 4-term polynomial which we can factor by grouping. So I end up with minus x squared times x minus 2 times x squared minus 4, and if I continue factoring, I see that x squared minus 4 becomes x minus 2 times x plus 2, which then becomes minus x squared times x minus 2 squared times x plus 2, right? So now I might say, okay, what are the zeros of this function, right? Well, the zeros are the x-intercepts, so that's where the entire function equals 0. That's going to be where each of its factors equals 0. So either minus x squared is equal to 0, or x minus 2 equals 0, or x plus 2 equals 0. Here, solving for x, I get 0, but notice because of the square, right, I'm going to get it twice, because I could rewrite minus x squared equals 0 as x equals 0 or x equals 0 in order to make that a true statement. So I'm going to abbreviate multiplicity as mult2. Here, with x minus 2, that equals 0 when x equals 2, but remember that was also a factor twice, so it's also going to be a 0 with multiplicity 2. And last but not least, x could equal negative 2 as a 0, and we're only going to have multiplicity 1, meaning that it only shows up 1. Okay, so notice, let's remember what we've got. We've got a 0 at 0 with multiplicity 2, and a 0 at 2 with multiplicity 2. All right, so let's take a look now at Google, and we're going to have to type in this new function. Okay, so we're going to get x to the 5th, minus x to the 5th, pardon me, minus x to the 5th, plus 2x to the 4th, plus 2x to the 4th, plus 4x cubed, plus 4x cubed, minus 8x squared, minus 8x, x squared. All right, and then we're going to graph that. So let's take a look at this. Ooh, notice that it's an x to the 5th, so its end behavior are opposite, right? It's facing opposite directions. And remember what we said. We said that the 0 at 2, positive 2, had multiplicity 2. The 0 at 0 had multiplicity 2. And the 0 at negative 2 had multiplicity of 1. Okay. All right. So we might draw from this some conclusions. If a 0 only happens as a, with a multiplicity of 1, notice what happens with the graph. It goes straight through. With multiplicity 2, it's touching but not really going through. You might say that around that 0, you have behavior like a parabola, right? X squared is a parabola, and so these factors that are squared are acting, like little parabolas around that 0 value. And the, multiplicity 1 is like a linear factor, right? So if you think about almost like a line going through. Not exactly, but that's a nice way to think about it. All right. What about if a 0 has multiplicity 3? Yeah. Well, in the next video, we'll talk about that.